So I'll be doing question 2 from test 2. We have a ball suspended from a string and it's moving in a circular path. The length of the string is L and the angle the string makes with the vertical axis is theta. And so the ball is also moving in a constant speed, and the only forces known to be acting on the ball are the string force and the earth. So when we have a circular motion problem like this, we know that because it is a constant speed, the parallel component of the rate of change of momentum for the ball is going to be 0. So that's A. And for part B, it says determine the magnitude of the tension in the string. So we know that we want dynamic equilibrium. We know the net force is going to be 0, again, because of this constant circular motion. So we'll start by drawing out this free body diagram of the ball, and we know that the force of tension, or the force of gravity, is pointing downwards, and then the force of tension is pointing up and to the right. And so we're trying to solve for force of tension. And so if we draw this triangle, we see that mg, this force of gravity, is going to be this axis, this vertical axis, and so we can solve using basic trig. We know that cosine theta is adjacent over hypotenuse, which is really mg over force of tension. And so in order to solve for force of tension, we are going to get the force of gravity in the downwards direction over cosine theta. So that is solving for the tension force. Then moving on to part C, says calculate the perpendicular component of the rate of change of momentum for the ball. So this is not going to be 0 like the parallel component. The perpendicular component is actually this force pointing inwards to the circles at all time during circular motion. And so in order to solve for this, we'll also use trig. So we can see that we have this triangle again, and this time we're solving for this bottom axis. And so we know that sine theta is opposite over hypotenuse, which is perpendicular force over tension force. So we just solved for tension force. So we can solve for perpendicular force, which is just tension force times sine theta. And if we go ahead and plug in tension force, we have mg over cosine theta times sine theta, which is actually just equal to mg tangent theta. So that's our perpendicular force. And we also need to remember this is in the n direction. I didn't write that down, but this is in the n hat direction. And so for part D, we need to calculate the speed of the ball. And so with constant circular motion, one of these key formulas we need to know is mv squared over r, which is equal to the perpendicular force. And so we have v in here so we can solve for speed, and we know our perpendicular force. So we can set mg tangent theta equal to mv squared over r. So if we go ahead and start solving things out for v, we're going to get v squared is equal to rg tangent theta, because that mass does cancel out. And so we have to take a step back and go ahead and solve for r before we do anything else. So if you come back up to our original diagram, using trig again, we can see that sine theta is just r over L. And so solving for r, we get r is equal to L sine theta. So come back down, plug that in for r in this v squared equation. And so we get v squared is equal to L sine theta times g times sine theta over cosine theta, which is just writing tangent theta out. And so we see under the radical we have, if we go ahead and take the square root of both sides, we have L sine squared theta g over cosine theta, which is actually going to set v equal to sine theta square root g times L over cosine theta. And so that is going to be our speed of the ball.